Okay, last video for this week then. So we're looking today at inequalities. And inequalities are equations that have sets of solutions. So they don't just have one solution, they have a whole range of solutions. So for example, x is greater than 5 means x can be any number bigger than 5, whereas an equation would just have x equals 5. So one solution, a whole set of solutions. Okay, so let's try an example straight away then. So for example, find the set of solutions for which 5x plus 9 is greater than or equal to x plus 20. So the way we solve this is the same as you'd solve a normal linear equation. So we're going to start by getting all the x's on one side and then all the numbers on the other side. So if we subtract x from both sides, we get 4x plus 9 greater than or equal to 20. And take 9 from both sides to get 4x is greater than or equal to 11. So dividing by 4 means x must be greater than or equal to 11 over 4. So this inequality is true for the set of solutions x is greater than or equal to 11 over 4. Now we can solve two or more inequalities at once, and the best way to do that is to sketch them. So to show you this as an example, we're going to try and solve two inequalities at once. So we're going to try and solve 3x minus 5 is less than x plus 8 and 5x is greater than x minus 8 at the same time. So we're going to solve both and then sketch the results on a number line to try and find the set that work for both of these inequalities. So for the first one, again, similar to the example we did before, we'll subtract x from both sides, add 5 to both sides, and divide by 2. So for this inequality we have x is less than 13 over 2. This one again, take x on both sides, divide by 4, so x is greater than minus 2. So two sets of inequalities, but what is the set that works for both of these? So we're going to sketch a number line. So for this value we have x is greater than minus 2. So there's a line representing minus 2, and x is any value greater than it. Here we have x is less than 13 over 2, so I'm going to do a separate line here representing 13 over 2, and x is anything less than it. Now, the range of values that work for both is the overlap. In other words, x is greater than minus 2, but less than 13 over 2. You always need to sketch these, or you're likely to get it wrong. Okay, so those are linear inequalities. We've got to also look at quadratic inequalities. So quadratic inequalities is very important. Again, you have to sketch these. Please don't forget to sketch them. And these quite often link to the discriminant. So remember, b squared minus 4ac less than, greater than, or equal to 0 tells you how many roots you have. So that's going to come into play with this topic as well. So we'll go through an example. So you can see we've still got our inequality sign, but now we have a quadratic equation. So I'm going to give you a step-by-step guide for how to solve these. So step 1 is always factorize. Step 2 is to sketch, and then step 3, read off the values. So for this one, we are going to first of all multiply everything by minus 1, because I want to have a positive x squared to make things a little bit easier. But there is a problem by when you multiply by minus 1 with an inequality. So before we try that, let's just show you why. If we have 9 is greater than 5, everyone can agree that's true. But if I times my inequality by minus 1, we'll end up with minus 9 is greater than minus 5, which is no longer true. So whenever you times by a minus or divide by a minus when we're looking at inequalities, you have to change the sign around too. So if you could put that into your notes, whenever you times or divide by a negative with inequalities, you must change the sign. So in this case, when we times by minus 1, we would then have to change the sign over. So that's what we're going to have to do in this example as well. So if I times all this by minus 1, we're going to end up with minus 3 plus 5x plus 2x squared is greater than 0. We can write this up to look a bit more like a quadratic. 2x squared plus 5x minus 3 is greater than 0. So we can factorise this one. So step 1, factorise. And we're going to get a plus 3 minus 1 there. So our x solutions are going to be x equals a half or x equals minus 3. Okay, so we factorised it. Next step is to try and sketch this. And you can do a really rough sketch when we're dealing with inequalities, just paying attention to the roots. So you've got one root at minus 3 and one root at half. Okay, so now we need to read off our values. So the whole question is said, find the set of values for which this quadratic is greater than 0. Now, 0 is where the y would normally be. So we're talking about the y for all of this. So for which x values is the curve, this quadratic, greater than the 0 on the y-axis? So if we have a look at this, there's y greater than 0 is all these bits. So we can actually think about getting rid of the rest of it. So which x values make y greater than 0? So you can see any x value here gives us a y value that's greater than 0, and any x value here gives us a y value that's greater than 0. So our sets of solutions for this one is x is greater than a half or x is less than minus 3. And your calculators, class whizzes, will do these two. If you go onto the inequalities mode, it will tell you these. But it's good to be able to sketch them and read off the sets of solutions that work for a quadratic inequality. Right, let's try a few more examples of these ones. Okay, so if you want to try this one, you're welcome to. It kind of combines the quadratic and the linear inequalities, but we'll go through it. So our first step, we're going to deal with the quadratic first and worry about this one later with a number line. So first up, our quadratic. So I'm going to rearrange to get everything on one side. So I'm going to subtract these two over here. So we get x squared minus 4x minus 12 is less than 0 because we've moved everything onto the other side. Then I'm going to factorise this, giving me x plus 2 and x minus 6. Next step was to sketch it. So we got a root at 6 and a root at minus 2. There we go. And we ought to find values for which this is less than 0. So less than 0 this time is all these bits we care about. So let's cross out all the bits that are greater than 0. Don't need any of that. So which x values make y less than 0? So it's going to be any x value between minus 2 and 6. There we go. Alright, so now we're going to do the same thing with our linear inequality. So like we were doing earlier, we'll add the 3 to both sides. divided by 5. So there's our set of solutions for linear inequality. So the set of values that works for both of these is going to be the set that includes a range of these values. So we're going to draw all of this on a number line. So first of all, the quadratic inequality, we go from 6 to 2 up to minus 2. Anything in there is allowed. And for the linear inequality, x can be anything greater than 1. So 1's about there, and there's our values. So the values that agree for both of these is this overlap here. So we can say x is less than 6, but greater than 1. And that set of solutions will work for both of those inequalities. Okay, let's try another one. If you really want to test, we're going to try 2 quadratic inequalities at once. So similar to this, but 2 quadratics. So if you want to pause the video and give this a go, you're going to need to solve 2 quadratic inequalities with the sketches, then do a number line with all your solutions and work out which values work for both of them. I'll go through that now, so pause the video and try it if you want to go. So we'll start with this one. So it's already all on one side, we're ready to jump in and factorise it. So to factorise this, we end up with 8 and 3. And it's going to be double minus on this one. So my sketch is going to look like this with root at 3 and root at 8. And we're saying when is the graph less than 0? So again, we can cross out everything we don't need. So when's the graph less than 0? When x is between 3 and 8. Okay, next one. So to factorise this one, remember it's a common factor kind of quadratic. So we're going to take out factor of x and be left with x minus 5. So to sketch this one, we're going to have one root at 0, the other root at 5. And this time we're looking for when is the graph greater than 0 on the y-axis. So that's going to be all of these values. So again, we can cross out the stuff we don't need. And we're left with 2 sets of solutions. So we have x is less than 0, or x is greater than 5. Okay, once you've got those sets of solutions, we can put all of this onto a number line and try and find out which values work for both of these. So the first one, 8 to 3. And the second one, we've got, I need some more room, let's try that again. So x is less than 0, or x is greater than 5. Okay, so we're going to try and solve both of those together on a number line. So for the first one, between 8 and 3. And for the second one, we've got less than 0, which is going to be over here. So there's no overlap at all. Or greater than 5. So 5 is here. So which bits overlap? The only region that works is this one. So our solution overall is going to be x is less than 8, but greater than 5. And that works for both of our quadratics. Okay, next up we're looking at discriminant inequalities. So we're mixing all of our inequality stuff with all of the discriminant stuff from a few videos ago. So just to recap, the discriminant is b squared minus 4ac. And because this sometimes greater than equal to or less than 0, it leads us to nice inequality questions. So we're going to jump in right away with an example. So find the set of values for which that has no real roots. So we're trying to find the set of k values, here's k and here's k, that make this quadratic have no real roots. So first key here is the no real roots bit, which means the discriminant is less than 0. Remember, you can't root a negative. So if we look through our quadratic and find the discriminant, remember A, B, and C. B squared is going to be 4k squared minus 4 lots of A times C, and that should be less than 0. So if we expand all this, we get 16k squared minus 8 lots of minus 5k is less than 0, so 16k squared plus 40k is less than 0. So we've got a quadratic. All we need to do now is solve this like we did in the last bit of the video, trying to find which k values actually solve this inequality. So both of these have a common factor of k. They've also got a common factor of 4. So I'm going to divide all of this by 4 to start with, leaving us with 4k squared plus 10k is less than 0. I can go one further and divide all of this by 2. So 2k squared plus 5k is less than 0. And now I'm going to factorise by taking out a factor of k. Okay, now remember, when we're trying to solve a quadratic inequality, we need to sketch it. And I know it doesn't have x's in it, but we can pretend that x and k are the same thing. And this is going to give us one root at 0 and the other root at minus 5 over 2. So let's draw on our quadratic. And we're looking for values at which this is less than 0. So less than 0 means you want the bit under the x-axis. So k is going to be between 0 and minus 5 over 2. So those k values make this quadratic have no real roots. Now some of you might be thinking, well, if the quadratic's got no roots, why does this one clearly have roots? And it's because this is not this quadratic. This is a quadratic purely made up from the discriminant of this one. So we've sketched, remember we sketched k on the x-axis here, whereas this is a normal quadratic with y and x in it. Common misconception though, just be careful, when you found the discriminant, the thing you're sketching is the discriminant. It's no longer the original quadratic. Right, let's try another couple of these ones. So next example, find the set of values for which this equation has 2 real roots. So if you want to pause it and give it a go, it's like the one we did just now, but obviously instead of no roots, we've now got 2 roots. Still going to be using discriminant inequalities to try and solve this though. So pause the video now if you want to try it on your own. Okay, so this time 2 roots means b squared minus 4ac is greater than 0. So positive discriminant because we've got 2 real roots. So b squared is going to be 8 squared minus 4 lots of k times c, which is 5k, should be greater than 0. So expand and simplify this one. So 8 squared is 64, minus 4k times 5k is going to be 20k squared is greater than 0. So I can rearrange this and add that to each side. So we're going to get 20k squared is less than 64. And I can now take it all to one side. So 20k squared minus 64 is less than 0. Divide through to get k squared minus 16 over 5 is less than 0. Okay, so if you want to sketch again and solve this one, it's going to be symmetrical quadratic this time. And our roots for that one are going to be k is plus or minus root 16 over 5. So root 16 over 5 and root 16 over 5. And this I'm looking for minus there as well. This I'm looking for greater than 0. So we're not interested in any of the bit in the middle. We care about this bit and this bit. So our solutions are going to be k is greater than root 16 over 5, or k is less than root 16 over 5. Now, because of, minus there. Because of surds, we could simplify that, so we could say k. So we find k is greater than 4 over root 5, or k is less than minus 4 over root 5. Okay, last bit for today, and then we're done for this week, is on shading, which I think you guys have already seen in GCSE, which is on shading regions. So occasionally with inequalities, we need to shade a region that satisfies a few different things. There's a few rules for these. So you can see when we've got a solid line, it means that value is included by the inequality. So for example, greater than or equal to, or less than or equal to, and a dotted line means it is not included by the inequality, for example, greater than or less than. So we're just going to try one example of this because it's quite straightforward. So we've got 4 different inequalities to satisfy on a graph. So I'll just get a bit more space. So first of all, y is greater than or equal to minus 2. Because that's inclusive, it means we're going to use a solid line. So y-axis, find minus 2, and we're going to have a solid line there. Y is greater than or equal to minus 2, so we're going to be shading things above this region. Next region, x is less than 5. So find 5 on the x-axis. And because it's less than, it's not being included. So we use a dotted line. Next up, y is less than or equal to 3x plus 2. So we need a positive gradient crossing the y-axis at 2, and because it's equal to, we're going to have a solid line. Something like that. And lastly, we've got x is greater than 0. So find 0 on the x-axis, greater than, so again it's going to be a dotted line, so we need to shade in this region here. So the region that encompasses all of that is the region in the middle here, bound by 2 solid lines and 2 dotted lines based on our inequalities. Cool, right, hopefully you understand all that. Could you guys try the quiz, and then we'll be moving on to a new topic next week.